So this topic, minimizing the number of states of DFA, which focuses on how to construct an efficient DFA. So for a particular regular expression, it would be possible for us to construct more than one DFAs. Okay, but out of those DFAs, which one which is going to be an efficient one, or which one which is going to be an most appropriate one to construct as a program, and that particular program which is going to act like what, lexical analyzer for us. Okay, and so this is going to be the flow actually. So you have regular expression. From the regular expression we are going to construct DFA, and you have possibilities of constructing more than one DFAs. Okay, for example, to this particular regular expression we are constructing two DFAs. One DFA which is going to have a total of 5 states, and another DFA which is going to have a total of 4 states. So just we have only one state difference, where one DFA which is going to have a total of 5 states, and another DFA which is going to have a total of 4 states. So among these two DFAs, we are going to choose the DFA, the second DFA, which is going to have a total of 4 states, and we are going to convert the DFA into program, and that particular program which is going to act like what, lexical analyzer for us. Okay, so our objective is to choose the DFA which is going to have minimum number of states. And then the next question is, how this two DFA which is going to gets differentiated. So how, on what basis we are going to differentiate these two DFAs. Okay, and then here we have an algorithm actually. So this particular algorithm which is going to convert or which is going to minimize the number of states of DFA. So actually we are going to take that particular DFA which is going to have 5 states, and then we are going to convert it into 4 states actually. So we are going to take DFA which is going to have 5 states, a total of 5 states, and then using this particular algorithm we are going to convert that particular DFA into another DFA which is going to have 4 states. Okay, so on what basis that we are going to make this conversion? So on what basis that we are going to convert this number of states, reduce the number of states from 5 to 4? On what basis that we are going to perform this? So for this we have algorithm, and in this algorithm we have some logic, as we are going to take a particular DFA, and then we are going to check it out what are the states which is working similar. Okay, so we are going to take the states which is going to work in a similar way, and then we are going to group that particular states into one state. For example, here we have the DFA with two states, states A and state C. We have two states. These two states which is going to work in a similar way. So it is going to receive a same input, and which is going to send the same output. Okay, so based on what it is receiving and what it is sending, so you have what in DFA, in deterministic finite automaton and diagrammatic representation, you have arrows. Those arrows we used to call it as labeled edges or else outer directed edges. So based on the label value passed through these arrows, or based on the transition that we have between these states. Okay, so what is the input message that it is receiving, and what is the output message that it is passing to other state? So based on that we are going to group the states, and after grouping the states we are going to consider only one of the state out of those groups, and then we are going to take that particular one state, and then we are going to use it and to the newly constructed DFA. So from an existing DFA you are going to construct a new DFA, and then we are going to apply that algorithmic logic to this existing DFA. And after applying this algorithm we used to get some subgroups of states, or we used to group those states. So how we are going to group those states? Based on the similarity, or based on how those states are working in a similar way. Suppose if one or more states work in a similar way, we used to group it as a single group, and out of those groups we used to take a particular state as a representative. Actually we used to call that particular state as a representative, uh, which used to be used in the newly constructed or newly constructing DFAs. So from a particular DFA, we are going to construct a new DFA, and we are going to apply some algorithm to that particular existing DFA. So what is the algorithm logic? In that particular existing DFA, we are going to check whether any of the states work in a similar manner. So suppose if one or more states work in a similar manner, we used to group it under a single group. Okay. So normally we used to have more number of groups over there, but we used to group those states under single group. For example, state A and C, which is going to work in a similar way, we are going to group it under a single group. And out of those A and C, we are going to take any one of the state, and that particular state which used to acts like a representative, and that particular state will be considered for the newly creating DFA, or whatever the DFA that you're going to newly create. Okay. So this is the simple logic that we have in that particular algorithm. So basically we used to call these new subgroups formation as a partition. We used to call this as a partition, partitioning the state behavior and then grouping it, and then constructing a new DFA. So that's the process that we have. So this is going to be the overall story that we have related to this minimizing the number of states of DFA. But it's very simple. Algorithm seems to be a little bit complex because they have used some various technical terms over there. But the logic is very simple. Just we are going to take a DFA, and then we are going to check whether one or more state which is going to work in a similar way. Suppose if one or more state which is going to work in a similar way, we used to group all those states under particular group, and after grouping we used to take only one particular state out of that particular group, and that will be used to the newly constructing a DFA. So we are going to construct a new DFA. We are going to consider that particular state to the newly constructing DFA. Okay. And then in this newly constructed DFA, you will have a minimum number of states. So comparing to the existing DFA, the newly constructed DFA, which is going to have some minimum number of states. So the objective is very simple. Just we have to construct a DFA which must have some minimum number of states. That's going to be the objective of this particular topic. Okay. So here you have some simple diagrammatic representation. With those diagrammatic representation, you would get the idea as how they have actually they have reduced the number of states in the DFA. Okay. And then here in this 2 DFA, you have some different names. So actually to differentiate, they have used some different names. For example, in DFA 1, you will have name with some alphabets. In DFA 2, you have state names with some numbers. Okay. And then in both the states you have different count of states. In DFA 1 you will have just 5 states, and in DFA 2 you will have some 4 states. So out of these 2 DFA, we are going to prefer a DFA which is going to have minimum number of states. So that's going to be the thing. And then out of these DFA, we are going to construct a table. We used to call it as a transition table. Suppose in that particular transition, normally we used to consider the transition table as an output for any DFA that we used to construct. And suppose if you are going to have the minimum number of states, automatically the table construction will be easier, and then it will be easy to construct program out of that particular transition table. And suppose if you're going to have more number of states, automatically the table construction seems to be a complex one. So normally we used to have DFA, and then we used to take construct into a table, and then further into a program, and that particular program used to act like what, lexical analyzer for us. But here we used to consider the DFA which is going to have the minimum number of states. Okay. And then there is a possible that for each and every language, for each and every regular expressions, you will have some minimum states of DFA. So you will have some minimum states of DFA over here. Okay. So you have some two diagrammatic representation. Um, move to the last slides, ma. Move to the last slides. So you have diagrammatic representation. Uh, you have DFA. Okay, stop with this. A DFA with 5 states. Okay. So this is very simple. This particular diagrammatic representation is very simple to understand. If you people have note and pen with you, you could draw it now in your note and pen. So because after drawing it in your notebook, you will get an exact idea as how it used to work. But see here, a total number of states that we have over here is what? 5 states. We have state numbers, state names A, B, C, D, and E. Okay, and then here we have to consider. So based on this particular topic, we have to consider the incoming label and then outgoing label. But normally, always we used to consider what? We used to consider the outgoing labels alone. Here we used to consider both the incoming labels and also outgoing labels. See here, the state A and C. We have two states, the state A and C, which is going to receive the input what? B, and then which is going to send the output what? A. And then to which state it is sending? It is sending the label A to the state B. So here both state A and state C, which is going to work in a similar way. What it is going to receive the input, the input which is going to be B. So from A to C, what we are receiving? We are receiving B. From C to C itself, it is receiving what? B. And then from E to C, it is receiving B. But what it is passing as an output? It is passing A as an output to the state B. Okay. So kindly concentrate in this particular diagram. So the state capital A and the state capital C, which is going to receive the input what? Input which is going to be small b, and then what is the output that it is going to send? It is going to send the output small a to which state? To the state B we are sending the label A. Okay. But we have only one difference, major difference between A and B. The difference is so where the state C, which used to receive two B's, two B. For example, C to C you will have an B, and then from E to C you will have an B. But somehow what it is receiving? It is receiving the label B. Okay. But here in A we are receiving a single B, and then what we are sending? We are sending A. Okay, we are sending the label A to capital B, and similarly the capital C, the state C, which is going to send label A to capital B. So what we are going to do here is we are going to take A and C, and then we used to put it into a particular group. Now we have two states in this particular group, A and C, which is going to be in single group, and then the capital B is state B, which is going to be in next group, and then D, which is going to be in another group, and then E, which is going to be in another group. So totally we have some four groups over there: A comma C, which is going to be the first group, and then D, which is going to be second group, and then E, which is going to be then another group, and capital B, which is going to be another group. So out of these four groups, further we are going to reduce into three groups here. So this is the logic actually that is being in this particular algorithm. So these types of creating a subgroup, we used to call it as an actually partitions. Creating a subgroup out of these diagrammatic representations based on the state functionalities, we used to call it as an what? Partitions. And after partition, now we are going to take the first group A and C. Out of this A and C, we are going to consider any one of the state. You could either consider capital A, or else you could consider capital C. Now again, now I'm going to consider capital A alone, and then I'm going to create a new group A, and then you will have B, and then you will have E, and then you will have what? D. So again I am creating what some four groups, and then here in this four groups just we are going to have what? We are going to have just four states over here. Now after this types of partition, now we are going to reduce the number of states from 5 to 4. Okay, so here the A and C, which is going to work in a similar way. So either we have to consider A or else we have to consider B. Now we are considering what? We are going to consider the A alone. For example, you could consider C, but for example, I am considering state A alone, where I am going to ignore what C. Okay, so that's the thing that we are going to do over here. And then see here in this diagrammatic representation, the B, the state B, which is going to receive some 5 input. So from A it is receiving input, from C it is receiving input, from B to B itself it is receiving input, from E to B it is receiving input, and from D to B it is receiving input. A total of 5A it is receiving, but it is sending a single B to the state what D. So based on the incoming arrows and based on the outgoing arrows, we have to focus. So here it is, we have some 5 incoming arrows. From A to state A to state B, you have what A, and from state C to B you will have A, and from B to B itself you will have a small a, and from capital E to B it is passing a small a, and from D to B it is passing small a, and finally it is passing a single output. What is the output it is passing? A small b from capital B to capital D. So it is receiving 5 input and it is passing at a single output. Okay, and next going moving to the state number D, state D, it is receiving a single input and single output. Okay, you will have a single input and then you have two outputs. Actually it is receiving a single input and it is passing some two outputs. The single input is from B to D, it is receiving what? B. From B to capital D, state B to state D, it is receiving B, and it is passing some two outputs. The output is small a and small b. So the small a which will be passed to capital B from state D to capital what state B. From D to B it is passing A, and from D to E it is passing B. By receiving input B it is passing two outputs B and A, and finally you have what the final state. Actually it must be double circled. The state E must be double circled actually. Okay, but here it is missing. We have to double circle the state E, which is going to be the final state. See here it is receiving B and it is passing B and A. It is passing B to C, small b from E to C, and small a from E to B. Okay, so all these arrows whatever that we have in the state B, which is going to be an incoming arrows. Actually the three labels, three A labels whatever that we are receiving, all those three A labels which is going to be an incoming labels. So at the bottom of this particular diagrammatic representation you have three A's, all those arrows which is going to be an input, input to the state B. Okay, but here in this diagrammatic representation we have to focus on just two states. For explanation purposes I have explained all these states as what are the incoming labels and what are the outgoing labels that we have, but here you have to concentrate just on only two states, the state A and state C. Okay, and then actually these two states which is going to work in a similar manner. So both these states which is going to receive the input B, and then which is going to send the output which is going to be what? A. Okay, and to which state it is sending? It is sending the output A to B, the state B. Okay, so that's going to be the process that we have to focus on. So the state A and state C which is going to work in a similar manner. Now we are going to group it as in subgroup. So A and C which is going to be in subgroup now, and further we are going to consider either capital A or capital C. Either we are going to consider state A or either we are going to consider state C. Okay, and then these types of subgrouping we used to call it as a partition, and after partition we used to take any one of the representatives out of these subgroups. So in the first subgroup we have state A and C. Either we could consider capital A or either we could consider capital C, and then we could use it for construction of a new DFA. Okay, move to the next slide. Move to the next slide. See here we have what? DFA with four states. So for the same regular expression for ARB to the power of asterisk ABB, for the same regular expression, so this particular diagram which is going to be the state with minimum number. So in the previous diagram, you have a total of 5 states. Here in this diagrammatic representation, you have 4 states. And then in the previous diagram, each and every state which is been named using alphabets. Here in this diagrammatic representation, we are naming the states using numbers. So the first state name is 1 2 3, and the second state name is 1 2 3 4, and the third state name is 1 2 3 5, and the fourth state name is 1 2 3 6. So we have 4 states. The first state is 1 2 3, and the second state is 1 2 3 4, and the third state is 1 2 3 5, and the fourth state is 1 2 3 6, where this the fourth state which is going to be the final state, or else we used to call it as an accepting state. Okay. Here normally we should differentiate as accepting state and non-accepting state. Basically we don't need those differences, but for some purposes they have actually differentiated as accepting states and non-accepting states. Okay. See here, in the previous diagram, state A and C, which is going to work in and what, which is going to work in a similar way. Here in this diagram, the work of A and C will be done by a single state 1 2 3. The first state 1 2 3, this particular state, the 123, this first state, which used to work similar to the state A and C, which is present in your previous diagram. Okay. So here and see what it will do. It used to receive the input B, and it used to send the output what, A. See here the similar thing. It used to receive the input B, and then here you have to do some changes ma. Here we have denoted B from the label B is passing from 1 2 3 to 1 2 3 4. It is not B, actually it is small a. Okay. Which is wrongly typed over here. So from state 1 2 3 to state 1 2 3 4, the label that we are passing here is A, small a, and not it is small b. And similarly, we have an transition between 1 2 3 6 to 1 2 3 4. The label that we are passing here is small e and not small b. So here in this slide, with these two labels, which is underlined with some green lines, these two b's, which is going to be an actually a, not b. Okay. With cursor you have what, a small b from 1 2 3 6 to 1 2 3 4. This is not small b, actually this is small a. Okay. If you have note and pen, kindly change it in your notebook. And similarly, from 1 2 3 to 1 2 3 4, we have what, a small b. This is not small b, this is a small a. Okay. So kindly make these changes. So here this particular state 1 to 3, which is going to receive the input which is going to be small b, and what is the output it is going to send? The output it is going to send is small a. So it is receiving the input from 1 to 3 itself, from 1 to 3 to 1 to 3 itself, small b, and then it is receiving one more small b from 1 to 3 6 to 1 to 3. Okay. And now it is passing the output to from 1 to 3 to 1 to 3 4. The output here is small a. Here in this slide, which has been mentioned as small b, it is not small b, it is small a. Okay. So the work of capital A and capital C in the previous diagram, which is done by a single state in this DFA. The state is what, 1 2 3, this particular state, which is going to do the work of two states of the previous diagram. So this is how actually we used to minimize the number of states of DFA. So with this two diagrammatic representation, we are coming to the conclusion. For each and every regular expression, you will have an unique DFA which is going to have some minimum number of states, and always we have to consider that minimum number of states DFA for constructing further into one program, and further that particular program which is to act like an lexical analyzer for us. Okay. So these two diagrams are very important thing. So based on these two diagrams only, actually the entire algorithm it used to work. So it's very simple. In both the diagrams we have what, states. In one of the diagram, the first diagram, we have represented the state names with alphabets as A B C D E, and here in the second diagram we are representing the states with numeric value as 1 2 3 1 2 3 4 1 2 3 5 and 1 2 3 6. And then what is the exact process that we are doing over here? We are going to minimize the number of states. So how we used to perform the first we are going to take the first DFA, and then we are going to partition it, or we are going to create some subgroups. Whatever the partitioning process that we are going to do over that, we used to call it as a subgrouping actually. And after subgrouping, we used to consider, or we used to take any one of the states from those subgroups. We won't consider all the states in the subgroup. Either we used to consider only one of the states from that particular subgroup, and that will be considered for the next DFA whatever that you're going to create as a new one. Okay. So comparing the previous diagram and this particular diagram, where in the previous diagram state A and state C, which used to work in a similar way. So how it used to work? It used to receive the input B, and it used to send the output A to the next state. Okay, from state A to state B, it used to send the label A. Similarly here, the state 1 to 3, which used to receive the input B, the input label which is going to be B, and then output it is going to pass here is A. Okay, from 1 to 3 to 1 to 3 4, it is passing the label A over here. Okay. So that's the thing. And then remaining states which used to work as a similar way. The state B in the previous diagram, which is to work similar to the 1 2 3 4 in this particular state. The state 1 2 3 4 in this particular diagram, which works similar to the state B in your previous diagram. And then the state D in your previous diagram, which is to work similar to the state 1 2 3 5 in this particular diagrammatic representation. And then the state capital E in the previous diagram, which is to work similar to the state 1 2 3 6 in this diagram. So some of the state which used to work as such, but we have two states A and C which used to work in a similar manner. So we are going to group it, and then from that we used to consider one particular state, and we used to consider it for construction in the newly constructed DFA. So here the capital state A and C, which is being converted into a single state. The single state here is 1 to 3. So this is going to be the single state that we have constructed from the previous diagram. Okay. So move to the first slide, ma. Go to the first slide. So here you have some so many descriptions regarding this particular algorithm minimizing the number of states of DFA. Here, instead of concentrating on much on this particular thing, now I'm going to concentrate on some specific things alone. Okay. So here, what is the regular expression that we are going to use? The regular expression that we are going to use here is A or B asterisk ABB. So this is the regular expression that we are using over here. So to recognize the same language, we are using this particular regular expression, and we are going to and then we are going to construct some two DFAs over here. Okay, these two DFA which is going to have some different state names. As in one of the DFA we are going to use alphabets, in another DFA we are going to use what? We are going to use state numbers, numbers as in state names. So we are going to construct some two DFAs, and then it is to be noted that always there is going to be an unique DFA, and then which that particular DFA which is going to have some minimum number of states. So that is very important here. And then always we used to prefer that particular DFA. So whatever the DFA which is going to have some minimum number of states, always we used to prefer that particular DFA. So that is very important over here. So the names of the states is not important. We are concentrating on the numbers of states. So how many number of states that we have in DFA, and then that too always we used to concentrate. So which DFA which is going to have the minimum number of states. So that's the thing. And then move to next slide, ma. Move to next slide. So here you have some comparisons between those two diagrams. So we are going to take states A and C, which is going to be actually equivalent one, and then so on what basis they are equivalent? They are not an accepting state, and both of them which is going to work in a similar manner. So that state A and C which is being uh, converted into a single state, what? 1 2 3. That's going to be the single state that we are constructing over here. So in the second DFA, the state A and C which has been combined and which has been converted into a single state, what, 1 2 3. And then the state B which used to works, which used to behaves like 1 2 3 4, and then state D which used to works like 1 2 3 5, and the state E which used to work similar to 1 2 3 6. By comparing those two diagrams, and then how they used to work, they are comparing this each and every state with the other states. Okay. And then though we are going to have two different diagrammatic representation, we are going to consider the diagram which is going to have some minimum number of states. Okay. The purpose of considering this minimum number of states is, so with this we would be able to construct some program which is going to be an efficient one, and that particular program just works like an lexical analyzer for us. um, so for the same language ARB asterisk ABB, we are constructing some two DFAs actually. See here in the bottom, they have mentioned A comma C, that's going to be the first group, and B within the braces, which is going to be the second group, and D within braces, which is going to be the third group, and capital E which is going to be the fourth group. Now what we are going to do, we are going to take the A and C which has been converted into 1 2 3, one state, and B which is going, which has been converted into what, 1 2 3 4, that's going to be the second state, and D which is been converted into what, 1 2 3 5, which is going to be the third state, and E which used to work like what, 1 2 3 1 2 3 6, which is going to be the fourth state. Okay. So that's the thing. So actually how we are creating a subgroups. So in the last line you have what, those subgroups descriptions as A comma C which is going to be a group 1, and B which is going to be another group, and D which is going to be another group, and E which is going to be another group. So these types of segregations we used to call it as an actually partitioning the states based on its functionalities. We used to partition the states. Move to next slide, ma. Move to next slide. So here in this particular slide, here we have to concentrate on, so on what basis we are differentiating, on what basis we are differentiating those states. So based on the functionalities we are differentiating those states. So you will have, so on what is the input that it is receiving, and what is the what is the output that it is passing. So based on those things we are distinguishing one state with another state. So how we are distinguishing those states, and how we are converting or constructing the minimum state equivalent DFA. And then so whenever we used to detect some input strings, so what is the normal logic that we used to use? We have to start from the initial state and we have to reach the accepting state, and whatever the pathway that we are going to use, based on the pathway that particular input string will get detected. Okay. So that's the thing. So here you have what those numbers like representation as 8, from 8 and then state 8 in this slide. That's not 8 actually, that's going to be actually 8, which is an S here. Okay. That's not 8, which is going to be an S over here. Move to next slide, ma. So here we have some examples. So in this example, those differences, actually the state C which used to receive some 2 B's, and the state A which used to receive a single B. Okay. So to differentiate that, they have given this particular description over here, where the double B which is been received by capital C, and then though it is going to receive some 2 B's, it used to pass a single A to the state capital B. Similarly here capital A which used to receive the single B, and then it used to pass single A to the state capital B. So how this particular algorithm it used to work, the state minimization algorithm which used to work by partitioning the states of DFA into groups of states. So we are going to partition it, and then we are going to create some groups of states. So this is going to be the main logic over this particular algorithm. Using this state minimization algorithm, we are going to partition, and then we are going to create some group of states, and further it will be converted into one single states. See here, so each group of state is then merged into a single state of minimum state of DFA. So this particular line is very important. So in this line, from the line number 5 till the line number 8, which is going to be very, very important one. The state minimization algorithm works by partitioning the states of DFA into groups of states that cannot be distinguished, and then each group of state is then merged into a single state of minimum state DFA. For example, we are partitioning, and after partitioning you have state A and C, and then we are going to merge it. How we are going to merge it? The A and C will be merged into one single state. The single state will be 1 to 3, the state 1 to 3 in the second DFA. So that's the process that we have over here. Mm, then move to next slide, ma. So we have some algorithms. The algorithm which is based on accepting state and non-accepting states. Normally we used to always concentrate on accepting states. Here each and every state which used to receive some input label, and also which used to receive some output, which used to send some output. So we are concentrating on non-accepting states also. We are not going to consider accepting states alone. Instead we are going to consider all the non-accepting states whatever that we have in this diagrammatic representation. Here in this slide you have some a equal to, that is not 81 81 8k, which is going to be s1 s2 and sk actually. Okay, s1 s2 sk, those things are actually the state numbers. So grouping the states, so what are the states that we have, so to denote those states which is being grouped. And then si and sj here which has been represented as 8i and 8j. So si, which is going to be the first state, and sj, which is going to be the second state. So si, which is going to be the sending state, and sj, which is going to be the receiving state. So based on the sending and receiving, we used to create some groups. Those groups being created, and actually we used to split those groups actually. So whatever we discussed, so all those things which has been described over here, the partitioning, and then we're going to create some groups, and then after creating we used to split that groups, and then further we used to construct into some into some single state. So those things will be there. Move to next slide, ma. Move to next slide. So in the next slide, you will have this algorithm minimizing the number of states of DFA. So already it's time up. So with this, I would like to stop the presentation. Okay. So I will explain about this algorithm in the next class. There will be some important things in this algorithm. So I will explain this algorithm in the next class. Okay. Thank you, students. Um, Thank you for listening patiently for the last 45 minutes. Thank you. Thank you for listening.